A single solar panel installed and tilted toward the sky. No moving parts, no emissions, no fuel, just light striking a precisely engineered surface built one variety of the grid. This is the product of everything you have seen today. As the day draws to a close, the factory continues without interruption. The same processes, the same sheaves, the same mesas, the same laminae. From above, the full scale of this operation becomes clear. Loading bays, production halls, warehouse wings, all in continuous coordinated motion. Even as trucks depart, the factory's quality oversight continues. Random panels from outgoing shipments are selected for additional testing, including accelerated aging protocols simulate use that the learning terms are open but talents they travel thousands of kilometers across continent oceans before reaching the installation sites where they will begin their working lives generating clean electricity. Each outgoing pallet carries a detailed manifest label listing the serial number, power test results of every panel it contains. A scanner confirms each label at dispatch, completing the chain of traceability that links every finished panel back to its raw material batch. In the warehouse, automated stacker cranes move pallets of packaged panels to their designated storage locations with precision and efficiency. The student pays for target date, place them navigates without hesitation. An automated packaging machine wraps and seals each panel pair in reinforced outer carton material, folding and taping every edge and seam. The result is a rigid, secure package that protects the panel from moisture, compression, and impact throughout its journey to the installation site. Is applied. These protectors absorb the localized impacts that corners are most vulnerable to during handling and transport, a detail that makes a significant difference in the condition of panels upon arrival. Panels that have passed all tests move to the packaging station. They are placed face-to-face in pairs with protective interleaving film between them, then wrapped in reinforced cardboard with corner protection. When a trend suggests that a process parameter is moving out of its optimal range, the production team investigates immediately. This continuous feedback loop, from test results back to process adjustment, all test data is fed in real time to the factory's central quality management system. Operators monitor production trends across every line and every shift, watching for any drifts in efficient issue requiring attention. The electroluminescence image shows the panel's internal condition with clarity that no other non-destructive technique can match. A healthy panel glows uniformly across its entire surface. Each panel also undergoes electroluminescence imaging. A current is passed through the panel in reverse, causing it to emit a faint glow. A sensitive camera captures this emission in detail, revealing the internal structure of every cell and every electrical connection within the module. The test results populate the display in real time. Maximum power output, open circuit voltage, short circuit current, and link to the panel's unique serial number, forming part of its permanent quality record for its entire operational life. The solar simulator fires. A single brilliant flash of calibrated light floods the panel surface uniformly, simulating full sunlight for a precisely controlled instant. Each panel is positioned automatically on the flash testbed, aligning the output contacts with the test probes. The positioning is precise to within millimeters, ensuring consistent contact and reliable measurement across every panel tested. Every completed panel, without exception, must pass a final round of electrical testing. The testing area is equipped with reproducing standard test conditions with the precision required for certified performance measurement. Before final testing begins, each panel receives a thorough manual inspection. A trained inspector examines every element of the finished assembly, checking for any visual defect. A visible quality issue is set aside for rework. Output cables are connected to junction box ports, one posited with an industry-standard weatherproof connector. These connectors allow the panel to be quickly and safely integrated into a solar array during installation, without any exposed wiring. The junction box lid is sealed with a pneumatic press tool, compressing a gasket around the entire lid perimeter. The resulting seal is weatherproof and rated for outdoor exposure, protecting its internal components from moisture, dust, and mechanical intrusion. Inside the junction box, ribbon leads from the panel's internal circuit are connected to the terminal blocks. Bypass diodes are also housed here, could allow current to flow around any shaded or damaged cell string, preventing the formation of damaging hotspots. With the frame secured, a junction box is bonded to the rear surface of the panel. Positioned precisely over the ribbon lead access points, the box is pressed into silicon held while it cures. This box is the panel's electrical interface with the outside world. At each corner, electrical section needed is sealed by CN compound. These corners are among the most stress-critical points of the entire panel structure, subject to repeated thermal expansion and contraction over its lifetime. A frame machine applies simultaneous pressure to all four frame sections, seating them uniformly in one coordinated motion. The glass are versatile. Corner joints tight and flush. Each frame section is fitted onto a panel edge, the glass sliding into the sealant-filled groove. The fit is snug and even, with each corner a metal corner key as the profile seats the adjacent frame sections together. Before the frame sections are fitted, a bead of silicone sealant is applied into the groove of each profile. This sealant will bond the glass to the aluminum and create a weatherproof seal that must remain effective through decades of thermal cycling, rain, and ultraviolet exposure. The aluminum arrangement of groove machined into the itch edge. These pearls are the structural skeleton of the finished panel, mounting and protecting the glass edge against impact and moisture. A trimming operation removes the excess encapsulant and backsheet material that extends beyond the glass edges. The trim tool runs cleanly along each side, leaving a precise flush perimeter that is ready to receive the aluminum frame. The laminated panel exits the machine as a single, rigid, unified structure. For the first time in the production process, what is clearly recognizable as a solar panel moves along the conveyor. Inside the laminator, a vacuum system removes all air from between the layers, while a flexible membrane, at around 150 degrees Celsius, the cap softens, flows into every space around the cells, and cross-links into a permanently bonded waterproof matrix. The completed stack is transferred into the laminator. Heat and vacuum will bond all layers into a single unified structure. Once the door closes, the transformation begins. The final layer, the back sheet, is placed over the second encapsulant sheet, completing the module stack. This durable multi-ething inside from moisture, ultraviolet radiation, and mechanical damage. A second sheet of encapsulant film is laid over the top of the cell strings, encasing them completely between two protective layers. The cells are now sandwiched within the encapsulant, ready for the bonding process that will seal them in place permanently. The strings are interconnected by soldering copper ribbons between adjacent string ends, completing the panel's internal electrical circuit. These inner string connections carry the combined current of all the cell strings and must be reliable, well-formed, and correctly positioned. The strung cell strings are positioned carefully on the encapsulant-covered glass, arranged according to the panel's electrical design. Each placement at deliberate accuracy. The geometry of this layout will be frozen permanently during lamination. A sheet of encapsulant film is unrolled across the surface of the glass. This transparent, slightly tacky material will eventually bond all the panel's layers together and protect the cells from moisture and mechanical stress for the panel's entire operational life. The assembly process begins with the front glass. The sheet of low-iron tablet is rebarred. Its immense engineered to withstand decades of outdoor exposure. The module layup and lamination area is the most spacious section of the production floor. A wide, clean, brightly lit space where the individual components of each panel are assembled into their final layered structure before permanent bonding. Before any string moves on to module assembly, its solder joints are checked by an automated vision inspection system. Any joint that falls outside specification triggers an immediate alert, and the string is diverted for rework. Completed strings of cells emerge from the stringing machines as neat rows of interconnected units, their blue surfaces aligned, their copper ribbons clean and consistent. Each string represents one section of the final panel's electrical circuit. Each solder joint must be strong, uniform, and efficient. Infrared heating minimizes thermal stress, forming a permanent low-resistance connection. Module assembly begins in the stringing area, where individual cells are interconnected by thin copper ribbons coated with solder alloy. Automated stringing machines pick up sensor to place throttles, align them with micron accuracy. Based on the test results, each cell is immediately sorted into a bin corresponding to its efficiency range. This process, called bin, so that every stainless are grouped together. Too much pressure risks cracking the fragile silicon. Too little produces an unreliable measurement. The probe system descends with controlled force, makes contact at the exact specified points, then lifts away cleanly. As each cell passes under the solar simulator, an intense flash fires. In the milliseconds of that flash, voltage probes in contact with the cell's bus bars measure its current full range of operating conditions, producing a complete electrical characterization in an instant. Every completed cell must be tested before it can proceed to module assembly. The cell testing area is equipped with automated flash testing stations, machines that simulate simulated burst of light. Emerging from the firing furnace, each cell is now complete. The deep blue surface to Gergen, what enters a photovoltaic device. With both sides printed and dried, the cells enter the firing furnace. A long tunnel rapidly heats them to around 8 feet, then cools them quickly. This causes metal paste to fuse permanently to the silicon surface, forming low-resistance ohmic contacts. After front-side printing, the cells pass through a drying oven that fixes the paste in place before the rear side is printed. This intermediate drying step ensures the front contact pattern is not disturbed during rear metallization. The front contact pattern consists of fine parallel lines, called fingers, connected by wider horizontal bars called as cards for extraction, balancing broad current collection against minimal shading. Screen printing uses a stainless steel mesh screen with a precise pattern cut into it. A silver-based conductive paste is forced through the openings by a squeegee in a single controlled stroke, depositing the exact pattern of contacts needed on the cell surface. The cells now move to the screen printing area, where conductive metal contacts will be applied to both surfaces. This metallization step gives the cell the current regenerator to occur in an external circuit. In advanced cell architectures, a complementary passivation layer of aluminum oxide is deposited on the rear surface using atomic layer deposition, building the coating one of uniformity and precision that no other deposition technique can match. The visual transformation is striking. Where once there was a matte silicon wafer, there is now a deep blue solar cell, its surface both beautiful and functional, designed at the nanometer scale to capture as much incoming light as possible. The anti-reflective coating gives the solar cell its most recognizable feature, the deep, rich blue color that has become synonymous with solar technology. This color is not a dye or a pigment, it is the result of the coating's exact thickness interacting with visible light. Inside the chamber, a plasma breaks down silicon nitride molecules and building a uniform layer approximately 75 to 80 out of the wafer surface, tuned precisely to cause destructive interference with reflected light. Wafers are loaded into the PECV chambers through automated ports. Once inside, the chamber silver vasa is about to begin, building a coating just nanometers thick but with a profound effect on the finished cell's performance. With the junction formed and the edges isolated, the wafers move into the PECVD coating area. Here, plasma-enhanced chemical vapor deposition machines An edge isolation step follows, using a precision laser to remove the unwanted phosphorus-doped material from the wafer's edges and rear surface. Without this step, the N-type layers work cleanly. After diffusion, the wafers are unloaded and transferred to the next processing stage. The PN junction has been formed, and the wafer thin is 30 is solar metal. The diffusion process is invisible. No light, no visible reaction, no dramatic transformation. Yet inside each furnace tube, phosphorus atoms are migrating into the silicon surface layer of the material. Wafers are loaded into quartz boats and inserted into the furnace tubes by automated loading arms. Once inside, they are exposed to a fullening gas that diffuses to the surface end of every solar cell. The textured wafers now move into the diffusion furnace area, where the fundamental electrical character of each cell will be established. Long-horizontal tube furnace right 8 a critical step in cell production. After texturing, the wafers are rinsed thoroughly in deionized water to neutralize and remove all chemical residue. They emerge from the rinse stations with a characteristic dark matte appearance, the visual signature of a successfully textured surface. The difference is immediately visible. A polished silicon wafer reflects over 30% of incoming light. A textured wafer reflects less than 5%. This single processing step has an enormous impact on how much sunlight the finished cell will ultimately convert into electricity. At the microscopic scale, the texturing process creates a landscape of tiny pyramids across the entire wafer surface. Each one, what was a mirror-like surface, becomes a highly efficient light trap. The first step in cell fabrication is surface texturing. Wafers are lowered into a bath of alkaline potassium oxide solution, which begins etching the silicon surface at microscopic level. The chemical reacts preferentially with specific crystal planes, and the transformation begins immediately. Wafers that pass inspection are organized into trays. Thin, flat, perfectly uniform, and gleaming under graduator, crawling under the factors or lighters. Automated vision systems perform a detailed inspection of every wafer as it exits the cleaning line, and laser scanners, From the ultrasonic baths, the wafers pass through a series of deionized water rinse stations, each one progressively purer. By the time a wafer exits the final rinse, its surface is chemically clean and ready for the next stage of processing. The wafers are immersed in ultrasonic cleaning baths, where abundance to clean, for slices perfing nova and jenny. The cleaning process thorough and genial. Handling wafers at this stage demands exceptional care. Robotic systems equipped with soft pneumatic grippers separate and transport each wafer individually, minimizing the risk of cracking or chipping that human handling would inevitably cause at this scale. The freshly sliced wafers emerge from the saw still held in formation, their edges perfectly aligned. Each one a unified silicon flat, the characteristic surface of a freshly cut crystalline material. The ingot is pressed steadily downward through the wire web at a precisely controlled feed rate. All wires cut simultaneously, and within a single operation. The cutting wire itself is a feat of engineering, ultrafine, often with dichrometers and a tight parallel formation across guide rollers, creating a web capable of slicing silicon with microscopic accuracy. The shaped ingot now enters the wafer slicing area, one of the most mechanically precise environments in the entire factory. Rows of multi-wire saw machines stand ready, each one capable. Nothing is wasted in this process. The cylindrical offcuts removed during shaping are collected, sorted, and dragged back to the melting stage. In acetals, this material recovery adds up to significant savings and reinforces the factory's commitment to efficiency. The cutting is extraordinarily precise. Diamond-coated wire removes material with minimal kerf loss, and the ingot's cross-section is transformed from a circle into a near square with clean drag it produces. The cooled ingot now moves to the shaping station. Diamond wire saws trim the cylindrical form into a pseudo-square cross-section, a shape that maximizes wafer area while allowing cells to fit together tightly within a finished panel. After the growth cycle is complete, the ingot is allowed to cool slowly in a controlled environment. The result is a large, silver cylinder of single volume in hundreds of kilograms. As the rod rotates and is slowly drawn upward, silicon atoms from the melt bond to the growing crystal in perfect order. The ingot takes shape gradually. A precisely oriented seed crystal is lowered on a rotating rod toward the surface of the molten silicon. The moment of contact is critical. The seed crystal introduces the atomic blueprint, the exact crystalline arrangement that the entire growing ingot will follow. Inside the sealed furnace chamber, the polysilicon has become something entirely different. What was once a solid, granular material is now a brilliant liquid pool, molten silicon. The furnace door seals shut, and the chamber is purged with argon gas to eliminate any risk of oxidation. Inside, temperatures begin climbing toward 14. With the polysilicon cleared for production, here measured quantities of the purified silicon are loaded into quartz crucibles, ready to begin their transformation inside high-temperature Jelski furnaces. Beyond the polysilicon, a wide range of supporting materials is received, inspected, and cataloged. Tempered glass sheets, rolls of encapsulant film, aluminum frame pros, judged, numbered, and stored in climate-controlled conditions until it is called to the production floor. Before a single gram of polysilicon enters the production line, it must pass a rigorous quality inspection. The Targetians extract samples from each incoming batch and feed them into spectroanalysis equipment. The process begins at the receiving dock. Sealed, pressurized containers arrive carrying one of two liters. Each container is filled with inert gas to prevent any contact with moisture or oxygen during transit. Inside, the factory floor runs with quiet, relentless precision. Automated conveyor belts carry materials from station to station. This is modern industrial manufacturing at its most refined. Every day, long before the world stirs, a massive factory comes alive. Stretching across acres of land, this facility is one of the most advanced Renewable tens of thousands of solar panels.